So, hi, welcome to our last full lecture. And you see I got my hat on. My house is chilly. So I'm wearing my hat and my scarf here to stay warm. So we've got the room number for both groups for the final. If you are at TU, your final is Saturday with everybody else that I teach. I teach 3 sections, and it's in the Science Complex, room 2226. That's 3 to 5 p.m. on Saturday. If you're tuned, there are just a few of you there left, I think. It's Monday, December 16th. The room number is 213. I think that's the room you've been having tests in, and it's from 2 to 4 p.m. on that Monday. Any questions about that? Okay. Well, tonight, our goals are to talk about transitive closure, because you will see a WebAssign problem. If you're in 8.2 and WebAssign, you've already seen it, which talks about transitive closure. So we're going to cover that topic, and then we're going to discuss equivalence relations. We've sort of snuck up on equivalence relations already, talking about Congruence Mod 4, but we're going to continue that discussion. And there are really 2 important things to understand about an equivalence relation on an underlying set A. Every equivalence relation induces a partition on A. What does that mean? It means there's a way to partition A up where we group together the elements of A that are all related to each other according to the equivalence relation. Conversely, if we have a partition of A, then we can define an equivalence relation where 2 elements are equivalent. In other words, A, B in the set A and little b are in the equivalence relation if and only if they're actually in that same partitioning set. Those are the little subsets that we union up to build the big set A. So if 2 elements are in the same subset of A, it's called a partitioning set, then they wind up being related to each other. So we're going to look at several exercises and make this, I hope, crystal clear tonight. Any questions before we start? All right, here we go. We're going to be in section 8.2. We're just finishing up 8.2 with this discussion about the transitive closure of a relation on a set A. Okay, so here's our definition. Given a binary relation, curly R, on a set A, we define the transitive closure of curly R. That's what we're defining, the transitive closure of this relation, curly R. And it's denoted by curly R raised to the power T for transitivity. So it's denoted by curly R to the T as follows. The definition is kind of interesting. It's a set theoretic definition. RT, or the transitive closure of R, is the smallest, and that's critical. It's the smallest subset of A cross A. So it's the smallest relation on A that satisfies 2 things. 1, curly R is a subset of curly RT. So the original relation is a subset of the transitive closure. In other words, all elements of curly R are in RT. That's the first thing. And then the second thing is that RT is a transitive relation. So the deal is this. The idea is this, was we might have a curly R that's not transitive. And just recall the definition of transitivity because we need to understand transitivity. Recall that put it up here. Curly R is transitive if, I'll write the definition with ordered pair notation. RST 1, 2, 3, we need 3 elements of the underlying set A. So for all little a, little b, and little c in the set big A, we have a compound hypothesis. AB being an element of curly R and BC being an element of curly R, those two things together imply that AC is also an element of curly R. In other words, if we see an ordered pair that has the element B as a second coordinate, but another ordered pair that has B as its first coordinate, in some sense we cross over on the B and we get AC in the relation. So we have an algorithm for finding RT. It's real simple. Remember, the first thing we want is that R is a subset of RT. So step 1 of the algorithm, remember an algorithm is just a sequence of steps or instructions that we follow. We include all elements of R in RT. We're building RT. So we start with the elements of R. We put them in there. And then step 2, we add any ordered pairs needed to make RT a transitive set. It needs to be transitive. It needs to follow this transitivity rule. And then step 3, we go back and check transitive closure with the new elements that we added. So go back and check that we have transitive closure. In other words, we have transitivity. Every time new ordered pairs are added, because some of them might force the hypothesis to be true with other elements. I'll show you what I mean in a minute. New ordered pairs. Go back and check transitive closure every time new ordered pairs are added. Until no more pairs are needed. That's when we quit. To make, well, needed for what? Needed to make RT transitive. You just keep going until you have enough ordered pairs that transitivity holds. Needed to make RT transitive. So let's play the game where we build the transitive closure of a particular set R. This is going to be our first example tonight. So find RT, the transitive closure of R, where R is a subset of A cross A, and A is the set that contains the elements 1, 2, 3, and 4. We can play all these games if we have 4 elements. That's all we need, is 4 elements. And curly R, the relation we're starting with, is the set that contains these 3 ordered pairs, 1, 2, 2, 1, and 2, 3. All right, so we're starting with this relation on A. It's not transitive, but we'll be able to find the transitive closure. In other words, we're going to include these elements and then add whatever pairs we need until we build a transitive set. So here's our solution. Step 1. RT is going to have, first of all, everything that's in R. So we'll put those elements in first. 1, 2, 2, 1, and 2, 3. But we're going to leave this open because we're going to look at step 2 and we're going to add ordered pairs to make it transitive. And we're going to use some scrap. Okay. So here's our scrap work. Let's take a look at the order pairs that we have and notice what we're looking for, folks. We're looking for an element of A that we're calling B that appears as a second coordinate in an ordered pair, but also appears as a first coordinate in another ordered pair. If we see that happening amongst these ordered pairs, we find a B, we cross over on the B, and we put AC in the relation. So, I see one right away. Do you see one right away where we've got a B that's a second coordinate in one pair and a first coordinate in another pair? Sure. Check it out, folks. We've got 1, 2 is in curly R, right? And we also have 2, 1 is in curly R. So our 2 is our crossover element. That's our B. So A is 1, B is 2, and C is also 1. Now we're going to look at the ordered pairs needed. We're going to see what we need to add. What ordered pair do we need to add to curly R as we're so that we're building RT correctly? We want to build this out so that it's transitive.
1, 1.
Yeah, we need 1, 1. We need AC. So we need 1, 1 in our curly RT, right? So let's go up here and let's add 1, 1. Can you see it okay? Is my red dark enough? I can try a different red. All right, but check it out, folks. These 2 ordered pairs, 1, 2, 2, 1, we could write them in a different order. We could say 2, 1 and 1, 2. If we write them in that order, then the B is the 1, and we cross over on that. What ordered pair do we need to add to RT?
Two, 2.
Sure. The A and the C are 2 and 2. So we need 2, 2. So let's go up here and add 2, 2. We're just going to keep on going until we add everything that we need. Can anybody see any other situation where we have the hypothesis of transitivity satisfied?
1, 2,
Amongst
2, 3.
What was that again?
1, 2, and 2, 3.
Yep, 1, 2, and 2, 3. We have 1, 2 in curly R, and we have 2, 3 in curly R. So what should we put in curly RT?
1, 3.
Sure. Now, every time we add new ordered pairs, there is the possibility of needing an A, comma, C, right? Because we have the possibility of satisfying this hypothesis every time we add another A, B, or B, C, because these can serve as either A, B, or B, C. So you might have noticed, hey, 2, 1 is in there and 1, 3 is in there. Let's just check that. I'm going to put it in a slightly different color. 2, 1 is an element of curly R, and 1, 3 is an element of curly R. Actually, I should probably put T's on all of these because we're really looking in RT now. And that says we need to cross over on the 1 and put 2, 3 in curly RT. But we already have 2, 3 in there, you see? It doesn't hurt to check. It's good to be real careful and just check and make sure that you get everything that you need. Can you see any other ordered pairs that we need to make this a transitive relation? We don't want to add anything we don't need. Like you could throw all the elements of A cross A into RT. It would surely be transitive, but it wouldn't be the transitive closure because that's got to be the smallest set that we can build, starting with R, that winds up being transitive. And I think that's it. I think we're done. So our final answer, after we've gone through and double checked that there's no element like 1 that's a first coordinate and a second coordinate. You might have noticed that 2, 1 and 1, 1 would yield that we need 2, 1, but we already have 2, 1. You don't ever have to use these reflexive pairs like 1, 1 or 2, 2 when you're trying to confirm the hypothesis of transitivity. These will never blow transitivity because A is equal to B. So if you have AB, excuse me, if you have AB, then you have BC already. So AC will follow immediately because A and B are equal because you have BC. So you have AC. Anyway, you don't need to use those transitive elements. I mean, these, reflexive elements, right? Like, you could check it. You could check, oh, I've got 1, 1, and I've got 1, 2. But 1, 1 and 1, 2, if you cross over on this 1, just tells you that you need 1, 2, and you've already got it. So there's no need to check with the reflexive pairs. What do I mean by the reflexive pairs? I mean the pairs that look like X, comma, X. You don't ever need to check with those. It'll never go bad. Transitivity. All right, symmetry also. So here we go. We have 1, 2, 2, 1, 2, 3. You could rearrange the order of these ordered pairs if you wish. If you want to put 1, 1 first, that's fine. This is a set. It doesn't matter what order. We put the elements, which are ordered pairs. But of course, within each ordered pair, the order of the coordinates matter. Excuse me, I am missing a page of notes. Pardon me. This happens very rarely, but once in a blue moon, I lose something. Well, I'm just going to have to try to wing it here because I know what I want to do next. The next thing I want to talk about is equivalence relations. Double check and make sure I don't have, okay. My goodness. Highly unusual. What are you going to do? So now we're in 8.3 and we're going to talk about equivalence relations and the very interesting properties that they have. So here's our definition. A binary relation, curly R, subset of A cross A, in other words, it's a binary relation on A, is an equivalence relation if it is reflexive, symmetric, and transitive. If we have all three of these, things work out really nicely. So here are a couple of facts. By the way, our primary example of an equivalence relation is congruence mod n. Just to remember from day 24 notes, this is day 25 today, we looked at congruence mod n. Now we're going to revisit congruence mod 4 tonight to give you a nice reminder about that. But this was our primary example of an equivalence relation. So you can review those notes. So we have two facts. Fact one. If we have an equivalence relation, and we'll play the game, on a set A, there is a partition of set A that R induces. In fact, the partitioning sets are constructed by placing elements of A that are related to one another in the same partitioning set, like the little AIs in the same partitioning set. Call it AI, A sub I. Remember we had like A sub 1, and A sub 2, and A sub 3. Well, the way we figure out how to group together the elements of A, if we have an equivalence relation, is we just group them together and put them in the same subset if they're related to each other by this equivalence relation. And it works out really nice. So this fact allows us to take an equivalence relation. Maybe that's what we'll do. We'll play the game. You're given an equivalence relation. And then what we do is we build out the partition. From that, we get a partition of A. I'll show you what I mean. It's real easy. So here's the primary, I'll call this example 2. The primary example of an equivalence relation was congruence mod n. Here's our example 3. We're going to play the game. So we're going to let A be this set, the set that contains 1, 2, 3, 4, 5, 6, and 7. Okay? Now we're going to build an equivalence relation so that we can practice getting the partition from it. We're going to define curly R, subset of A cross A, as follows. Here we go. This is our equivalence relation. Curly R has these ordered pairs. It's a set. So we need set brackets. Here we go. 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, 4, 4, 4, 5, 4, 6, 5, 4, 5, 5, 5, 6, 6, 4, 6, 5, 6, 6, and finally 7, 7. Now we can check that this is an equivalence relation. So 1, let's just go through a check. Check that curly R is an equivalence relation on A. Once we have verified that, then we'll play the partition game. So we've got to check that this curly R is reflexive, symmetric, and transitive. So here's our check. Let's check reflexivity first. Which elements do we need to check that are in curly R that are the reflexive elements that make it a reflexive relation? Do you remember? Here's the relation. Here's the definition for reflexivity. For all elements little a in A, we need the order pair little a, little a to be in R. That's reflexivity. Every element needs to be related to itself. So what should we check? Which elements are going to help us figure out that curly R really is reflexive?
Elements that have the same number for both order pairs.
That's right. So we've got, and we need all 7 of them. Notice 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7 are all in curly R. If we were missing even one of those, then reflexivity would fail. It's a universal property. It has to be true for every element of the underlying set. So we definitely have what I call reflexive pairs here. We've got them all. 5, 5, 6, 6, 7, 7. We've got them all. All right. So now let's check symmetry. Remember what symmetry says. Symmetry says for all A and B in the underlying set A, if A, B is in R, then that implies that B, A is going to be in R. Right? We need the symmetric twin. If A is related to B, we need little b related to A. So as we scan through these elements of this relation, we don't even need to look at the elements that have the same first and second coordinates, because if A is equal to B, then both AB and BA are already in there. They're the same ordered pair. It's just A, A, right? If A and B are the same. But these other elements where A and B, the first and second coordinates are different, there's something to check there. We need to check that their symmetric twin is in there. So let's start with, well, as we scan through 1, 2 is the first one. It's in curly R, but also 2, 1 is in there. So that works out. Both of these are checked off now. They've got their symmetric twins. So we keep scanning. 2 2's no problem. 3 3's no problem. 4 4's no problem. But we have 4 5 in there. Well, that means we need 5 4 in there because, you know, A, B, B, A, and we have it. So as we continue to check symmetry, we see that 4 5 is in curly R, and its symmetric trend 5 4 is in curly R. So those are good to go. That takes care of this one and this one. What's next?
4 6.
Yep, 4 6 is the next one that's got different first and second coordinates, and its symmetric twin. 6 4 is there. So that takes care of 4 6 and 6 4. The next one is 5 4, but we've already checked that with 4 5. So it's good. 5 5, no problem, nothing to check. 5 6. Okay, so there's something to check there yet. 5 6 is in curly R. What do we need also to check for? What are we looking to see?
6 5.
And it's there. And that does the symmetry check. Now, transitivity. It's a pain. It's the most involved of all. I'm going to let you do that later because it'll give you good practice checking that this is actually this is actually a transitive set. So you do later. You can trust me. It really is transitive. You can check that, in fact, this curly R is equal to its own transitive closure because, i.e., curly R is already transitive. There's nothing that we need to add to make it transitive. So if you trust me that this is really a transitive set, then suddenly we've got an equivalence relation, and we can play the game where this fact says, hey, if you've got an equivalence relation, you can find the partition that it induces. So let's do that now. 2, find the partition that curly R induces on A. That's the way we say it. We say curly R induces a partition on A. So I want to show you a little bit of notation. Because we have a notation that helps us talk about these subsets that are going to be the elements of the partition. Given an element, say little a, in the underlying set A, so it would be like 1 or 2 or 3 or 4 or 5 or 6 or 7. Given one of those, this is our definition. We define square bracket little a, it's called the equivalence class of A, to be the set of all the elements X in A such that A is related to X, or AX is an element of the relation, where curly R is an equivalence relation on A. We can only play this game if we have an equivalence relation. Square bracket A is called the equivalence class of little a. It's the set that it lives in with all the elements of of A that it's curly R to. It's the equivalence class of the element little a. Okay. So let's go for a solution here. We're going to find this partition. Basically, we're just looking at the elements of A and we're asking, what are they related to? So let's find the partitioning sets. Those are the subsets that live in the partition. They're called the partitioning sets, i.e., let's find the subsets of A that consist of elements of of A that are related by curly R. These are actually the equivalence classes. They're actually the equivalence classes. Okay, so we can see curly R at the top. So let's do some scrap work and let's build out the equivalence classes. Okay, I'm going to fold this so we have a little more room. There's our curly R. Here's our notation for equivalence classes. And those equivalence classes are going to let us build this partition. That's what we're doing. We have an equivalence relation. We're going to build the partition. How do we build the partition? Well, we got to find the sets that live in the partition. So let's think about the first element of A. It's 1. So we can put 1 in square brackets and try to think about all the elements of A that are related to 1, because by definition, the equivalence class of 1 is all the elements X in A that are related to 1. You know, 1 is R to X, or 1 comma X is in R. But of course, R is an equivalence relation. So if A comma X is in R, then X comma A will be in R. And A comma A is in R because of reflexivity. It's an equivalence relation. So we know that the first element that 1 is going to be related to is itself. Every element has to live in its own equivalence class because of reflexivity. Does that make sense? Any questions before we look for other elements in A that are related to 1? First one is 1 itself, because 1 comma 1 is in this equivalence relation, isn't it? All right, what other elements of A are related to 1 as you scan through these elements of curly R?
Ordered pair 1, 1.
The ordered pair 1, 1 says that 1 is related to itself. So we've already put 1. This is the first element of the equivalence class of 1. Maybe I need to make this one shorter so you can tell it's the same one I'm talking about right here. It's already in there because of 1 being related to itself. Are there any other elements of A that are related to 1 from these ordered pairs?
2.
2 is related to 1. See, because we have 1, 2. And of course, because of symmetry, we have 2, 1. So 2 and 1 are related to each other. 2 is related to itself. 1 is related to itself. Are there any other elements in this equivalence relation that are related to 1 or 2 besides just 1 and 2? See any other ordered pairs that involve a 1 or a 2? Nope. So that's it. This is the equivalence class of 1. It's related to itself and it's related to 2. By the way, we can also call this the equivalence class of 2. Their equivalence classes are the same set. They're related to each other. See that? That's going to be one of our subsets in our partition. We're breaking A up. We're grouping the elements of A together because they're related to each other. How do we know when they're related? Well, we just look at the ordered pairs in the relation. Let's look at the next element that we haven't dealt with yet. How about 3? As we scan these ordered pairs, what is 3 related to? What ordered pairs is 3 involved in with other elements or itself?
3.
It's only related to itself. It has to be related to itself because symmetry says, hey, 3, 3's got to be in there. So like I said before, if we're looking at the equivalence class of 3, 3 is going to be in there for sure. There might be other elements, but in the case of 3, there aren't any other elements of A that are related to 3. It's only appearing in the 3, 3 ordered pair. So the equivalence class of 3 only has 3 in it because it's only related to itself. Does that make sense? Let's look at 4. We're looking at the equivalence class of 4. We're looking for elements of A that are related to 4. What do you think? What's going to be in the equivalence class of 4?
4.
4 for sure, because 4 is related to 4. What else? Anything else?
5,
5.
6, and 7.
5, because 4 is related to 5, and 5 is related to 4. 6, because 4 is related to 6, and 6 is related to 4. And of course, 5 is related to itself, and 6 is related to itself, and transitivity means 5, 6, and 6, 5 are going to be in there. They have to be because if they're all related to each other, we have to have all the different ordered pairs that involve those 3 elements. Anything else related to 4? That's it. Now, but just to be consistent, we could call this the equivalence class of 5. We also could call it the equivalence class of 6. They're all the same class because they're all related to each other. So somebody said something about 7. Yes, we got to deal with 7. It hasn't appeared yet. This has got to be a partition of A, so every single element's got to appear in one of these subsets we're building. What is 7 related to, folks?
Just 7.
It's only related to itself. So it's sitting there all by its lonesome in a little singleton set. So finally, we are ready to write our solution. We have found the partition. We'll call it curly P. It's a set of subsets. We've got the subset 1 that's got 1 and 2 in it. We've got the subset that has 3 in it. We have the subset that's got 4, 5, and 6 in it. And we have the subset that has 7 in it. And then we close up the big set brackets. By the way, these are called the partitioning sets. They are the equivalence classes. We have 4 partitioning sets. You could call them A1, A2, A3, A4 if you wanted to. But they are the equivalence classes. That's our big fat hint. The partitioning sets are the equivalence classes. Because that tells us what's related to each other. Now, folks, we can play this game in the other direction. What am I talking about? The game we just played was we were given a binary relation and we found the partition that goes with it. But we can play the game where we're given the partition and our job is to find the equivalence relation that is corresponding to that partition. So let's play that game. Let's write down the fact. It's fact 2. This also appeared in our goals tonight. So here's our fact 2. Given a set A and a partition, we'll call it curly P, partition, and maybe it's got like A1, A2, I'll just put dot, 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 because it might be infinite, but it might be finite, a partition of A. There is an equivalence relation. Associated with the partition curly P. This relation call it R, and it's a subset of A cross A because it's an equivalence relation on A, has ordered pairs according to this rule. Basically, if you see elements of A sitting together in one of these subsets, then you have to make them related to each other in every way possible. Here's the rule. If little a and little b from set A are in the same partitioning set, A sub I, maybe just call it A sub I. If they're sitting in one of these together, then we need these ordered pairs in curly R. A comma A, B comma B, A comma B, and B comma A. We need all of these to be added because if they're in the same subset together, they're related to themselves and they're related to each other. So this is the way that we play the game where we're given a partition and our job is to build the equivalence relation that's associated with that partition. So let's play the game in that direction. Okay? Any questions before we start? All right, here we go. Example 4. Let's let A be the set that contains, I'm not going to make it so big this time. Let's say 1, 2, 3, 4, and 5. Okay, because this is going to take some time. Consider this partition of A. So we're going to be given the partition. The partition curly P is equal to, well, the first set has 1 and 4 in it. And the second set has 2, 3, and 5 in it. So it only has 2 partitioning sets. If you wanted to, you could call this one A1 and you could call this one A2. Now we've played the game with partitioning sets before. We've looked at collections of sets and we've asked, hey, is that actually a partition? What we'd like to do here now, though, because it is a partition, is find the equivalence relation curly R, it's going to be a subset of A cross A, that is associated with this partition P. So that's our job, is to look at these subsets and understand this. If elements are together in a subset of the partition, so they're in the same partitioning set, they're 2 partitioning sets, they have to be related to each other in every way possible. That means we need all these. So let's go ahead and do this. Let's solve this. We're going to build curly R. We're going to put in ordered pairs according to what's related. So does anybody have a wild guess maybe at one of the first ordered pairs that we could put into curly R by looking at this first partitioning subset or set A1? 1 and 4 are related to each other and to themselves.
1, 4.
Yep. 1's related to 4. 4 is also related to 1 because we need symmetry. We need reflexivity too. We're building an equivalence relation. So what other ordered pairs should we add?
1, 1, and 4, 4.
You got it. We need 1, 1, and 4, 4 as well. So like I said, these are the 4 ordered pairs that we get just by having 2 elements related to each other. How are they related? They're in the same partitioning subset together. They're in the same part. I call them partitioning subsets, but I think that they're actually called partitioning sets. Anyway, these subsets that are the elements of the partition. All right, so that's all, and that takes care of this first partitioning set, this first subset of A. Now we've got to deal with the second subset of A. All these are related to each other in every way possible. 2 is related to itself, it's related to 3, it's related to 5. 3 is going to be related to itself and to 2 and to 5. You get the drift, right? So what are some ordered pairs that we need to add to keep going to build R out?
2, 2, 2, 3, and 2, 5.
2, 2, 2, 3, and 2, 5. That's excellent. That takes care of all of the elements where 2 is going to be the first coordinate. What else do we need?
3, 2, 3, 3, 3, 5.
Yeah, we got to play the same game with 3. It's related to everything in there, including itself. So there's 3 ordered pairs with 3 as the first coordinate. And then?
5, 3, 5, 5, 5, 2.
Exactly. Very nice. And these are all the ordered pairs physically possible by mixing and matching the 2, the 3, and the 5 in every way possible, right? There's 3 choices for the first coordinate and 3 choices for the second coordinate, except we've got overlap when the first and second coordinates are equal. That's still 9 elements, actually. So it is 3 times 3. Questions? So you see, what we're seeing is something very essential about equivalence relations. They split up the underlying set A into subsets, where the elements that are in subsets together are the elements that are related to each other. So I'll give you a do later because you're going to want a little more practice, and you can bring, questions to office hours. Let's make our A just a tiny bit bigger. Let's put 6 elements in A. Here's example 5. I'm going to give you R. Here we go. It's going to have 1, 1, 2, 2. I'm going to go on and put all the reflexive elements in because I'm building an equivalence relation. 3, 3, 4, 4, 5, 5, 6, 6. Okay, reflexivity is taken care of. But then we're going to add 6, 4, 4, 6, 2, 3, 2, 5, 3, 2, 3, 5, 5, 2, and 5, 3. Find the partition of A that curly R induces, or find the partition that curly R induces on the set A. Okay? And then to go back the other way, just to be thorough, we're going to be given a partition P, and here's what it looks like. 1 is alone in a subset, 2 is alone in a subset. But 3, 4, 5, and 6, I know that's mean of me, are all in a subset together. So I know that's very mean of me, but there it is. You can, and if you can see what needs to be done, then that's great. So I hope that these couple of exercises have clarified to you kind of an essential thing that an equivalence relation does. And with this idea in mind, let's go back now and let's revisit Congruence Mod 4, because that was something that we looked at on Monday, but we can revisit it now, maybe with this deeper understanding, and we can ask similar questions. And one of the things I want you to keep in mind as we play Congruence Mod 4 games is 4 doesn't have to be the number that is the modulus. We could, this is the divisor. We're dividing by 4 and we're checking out the remainders. We're grouping integers together if they have the same remainder. Recall, this is the definition of Congruence Mod 4. It's a congruence. It's an equivalence relation on Z. It's called congruence because it has something even more than reflexivity, symmetry, and transitivity. It's got what we call left and right cancellation. You don't need to worry about that, but in case you're wondering why it's not called equivalence mod 4, it's actually a more structured relation than just an equivalence relation. It's called a congruence. But anyway, it's also an equivalence relation. Every congruence is an equivalence relation. And it goes like this. A is congruent mod 4 to B. That was our notation. If and only if 4 divides A minus B. So as we have our discussion tonight about congruence mod 4, it might be helpful if we think about a number line. Okay. So here's 0, 1, 2, 3, 4. 5, 6, 7, 8. It can be helpful to understand what's really going on with congruence mod anything. Here, the modulus is 4. We're dividing by 4. And we're thinking about which integers give the same remainder when they're divided by 4. Like all of the ones that I've numbered here, -12, -8, -4, 0, 4, 8, all of these that I've actually written down, they give the same remainder when they're divided by 4, don't they? When you divide these by 4, what remainder do you actually get, folks? Any of these?
0.
Yeah, I mean, these are the remainder 0. So what we want to do in this example 7, my blue pen out, we'd like to find the required elements of Z or subsets of Z as indicated. Okay, so I'm going to set this up and we're going to use this number line sort of as a reference. 1. Can you find a positive integer A such that A is congruent mod 4 to 7? So we can find 7 on our number line, and we can think about what 7 is. Here's 7. Let's think about what it means to say 4 is going to divide A minus 7, because B is 7 here. That means the distance between 7 and A, wherever we pick A, needs to be positive, so we're going to pick A on the positives. The distance between A and 7 is a multiple of 4. In other words, we get to it by jumps of size 4. So like 7, 6, 5, 4, 3. That's a jump of size 4 from 7. Or if we jump this way, 1, 2, 3, 4, we get to 11. And we can just check. This congruence groups together integers that yield the same remainder when divided by 4. Remember, 7 is 4 times the quotient plus a remainder. What is the quotient and what is the remainder? Anybody?
Quotient is 1 and the remainder is 3.
Yeah, the remainder's 3. And I'm saying that this particular definition turns out to group together or relate, make congruent integers that have the same remainder when they're divided by 4. Well, let's look at 3. 3 is equal to 4 times some quotient plus some remainder. What's the quotient, everybody? What's the remainder? Remember, the remainder has to be positive.
Quotient 0 and the remainder is 3.
Yeah. See, they're related to each other. And same with 11. And what would be the next one if we kept going, if we jumped another jump?
15.
Yeah, because 11 plus 4 is 15. And you can check it. 11 is 4 times 2, plus the same remainder. 15 is 4 times 3, plus that same remainder, namely the magic remainder 3. So possible solutions, we just want to pick an A, right? We could pick A equals 3. But isn't 7 congruent to itself? 4 divides 7 minus 7 because 7 minus 7 is 0. So 7 would work, 11 would work, 15 would work. I think 3 is the smallest positive one that would work. These would all be solutions. All right, let's move on. Let's find a negative integer, A, such that A is congruent mod 4 to 7. A is congruent mod 4 to 7. That's how we say that. Anybody? You know, we just keep jumping until we get into the negative range. That's why the number line's so helpful.
-1.
Yeah, -1. What's another one?
-5.
Yep, -5 because we're jumping by jumps of size 4. See, the distance between -5 and 7 is 12. It's a multiple of 4. 4 divides that. That's what I mean by these jumps of size 4. Every fourth integer is related to every fourth integer. Let's do another one. Let's find a positive integer B such that -2 is congruent mod 4 to B. So now we're going to look at, we can look at -2. What is the remainder when we divide -2 by 4? Let's just get an idea of what the remainder is.
2.
Yeah, it is. Because this is one of the times where you have to go backwards and over. So we have to kind of, from 0, we have to get to -2, we have to over jump to -4 so we can come back with a positive remainder of 2, because -4 plus 2 is -2. So here we are at your -2, right? So it's a remainder of 2. So jumps of size 4. We're wanting to find a positive integer. So let's go this way. 1, 2, 3, 4. Or 1, 2, 3, 4. What numbers are those? What's this first one?
2.
And then,
6.
yep, the possible solutions. B equals 2 or 6. The next one would be 10. Then 14. See what I mean? Every fourth one. Just to be thorough here, let's keep going. Let's find a negative integer B. Is everybody following this? That -3 is congruent mod 4 to B. So now we're thinking about, remainders mod when we divide, by 4. These ones had remainder 2 up here. What's the remainder when we divide -3 by 4? Let's see. -3 is 4 times some quotient plus a remainder. Remember, the remainders have to be 0, 1, 2, or 3. So what's the remainder when we divide -3 by 4? Well, what's our quotient? For question.
-1.
Yeah, we got to overshoot and get down to -4 so we can come back with a positive remainder of 1. So here R is 1. Here R was 2. Here R was 3. So we're looking for the elements that yield a remainder of 1, and we want a -1. So what's another negative? What is a negative number that yields the remainder of 1 when it's divided by 4? We're here at -3. Well, isn't -3 negative? I'll start with that. -3 is negative. And isn't -3 congruent mod 4 to itself? It yields the same remainder as itself. And 4 divides -3 minus -3, because -3 minus -3 is 0. 4 divides 0. Every one of these integers is related to itself. So you could just take b equals -3. But we want some other ones, maybe. We're going this way. What's the next one? Moving to the left. We want negative ones.
-7.
Yeah, good. -7. And then -11, right? -15, and so on and so forth. Jumps by jumps of size 4. All right, now let's practice our notation. Let's find the equivalence class of 0. What am I talking about? Equivalence class of 0, remember, it's all the integers, because the underlying set is the integers that are related to 0 by congruence mod 4. So let's just think about it. We're looking for all the integers that would yield the same remainder as 0 does when we divide it by 4. Or you can think about it as integers that are separated from 0 by a distance that's a multiple of 4. But these are the very first integers that I wrote down. These are all the multiples of 4. They all yield, what's the remainder that they yield again when we divide them by 4?
1.
No.
Oh,
Zero.
of 0.
Yeah, it's 0, because 0 divided by 4 yields a remainder and quotient of 0. When you divide 4 by 4, quotient is 1, remainder is 0. Divide 8 by 4, the quotient is 2, remainder is 0. So it's all of these. So that's one way to write this. You could say, okay, it's dot, 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 like -12, -8. You show enough of them. -4, 0, 4, 8, dot, dot. You know, that's enough to show that you know what elements are related to 0, mod 4. But nobody wants to write that. We have a better notation. Do you remember when we talked about congruence mod 4 on Monday, and when we had the QR theorem, we did this. When the divisor is 4 and we take a look at the integers, what happens? If we think about the remainders, we called the multiples of 4 4z. The elements of z that yield a remainder of 1 when you divide them by 4 was the set 4z plus 1. What's the next set called? These are the equivalence classes, mod 4.
4z plus 2.
Good. And what's the other one called?
4z plus 3.
That's right. Remember, because these were where the remainder is 0, integers that yield a remainder of 1, a remainder of 2, or a remainder of 3. So what we really want to probably do is write this as 4z. That's the best notation. Let's find the equivalence class of 1. Well, according to this, it's elements that look like 4 times some integer plus 1. It's 4z plus 1. Find the equivalence class of 2. Oh, it's the elements that yield a remainder of 2. When you divide them by 4, they look like 4z plus 2. Find Equivalence class of 3. Oh yeah, it's 4z plus 3. Finally, let's find the partition that congruence mod 4 induces on z. There are a couple of different ways we can write this. We have the notation where it's equivalence classes of the remainders, or we can use the set notation. The partition, you could write it as equivalence class of 0, because we know what it is, equivalence class of 1, equivalence class of 2, and equivalence class of 3. These are sets, okay? These indicate sets. Or you could write the partition kind of the way I like to write it, because this tells us more. I mean, once we see that there's 4 remainders, 4 equivalence classes, now we realize we're dividing by 4, but it's nice to see 4z, 4z plus 1, 4z plus 2, and 4z plus 3. Notice I'm not putting 4z inside set brackets because 4z is the set, multiples of 4, the integers that are multiples of 4. You don't need set brackets around it. This represents the set the same way that z represents the set that we understand. We don't put square curly brackets around z. We just write z. Questions? So I just want you to think ahead that we don't have to play this game with 4. We could play this game with other divisors. Congruence mod 2. The divisor that we're dividing by is 2. A, B, oops, let me use the notation. A is congruent to B. Mod 2, if and only if 2 divides the difference. That splits the integers up into the evens and the odds, because there's only 2 remainders. Every other, right? If 2 divides the difference, then you're going to every other integer. So you're jumping from even to even to even, or from odd to odd to odd. But I want you to also just imagine thinking about congruence mod 3. So the divisor that we're dividing the integers by is 3. And we know that that yields 3 possible remainders, so it splits the integers up into 3z. So these are like 3, 9, 12, -3, -15, 3z plus 1, 4, 7, 10, 1, -2, -5, jump by jumps of size 3 instead of 4 or 2. See what I mean? And these would be integers like 5, well, 2, 5, 8, 11. Go backwards, -1, -4, jumping by jumps of size 3. So A is congruent mod 3 to B if and only if 3 divides A minus B. Remember, A minus B is the actual distance between A and B on the number line. Saying 3 divides that means you can get between A and B by jumping by jumps of size 3, right? Do you get it? So you could see, congruence mod 5 on the final, or congruence mod 3, or you could see congruence mod any, reasonable, divisor that's not, too huge to make too much work for you. Questions? Well, I want to thank you for playing. I'm going to post this worksheet. You've got WebAssign. I want to just add a couple of things to the worksheet 8. It'll go up. And I'll also be creating a review sheet for the final exam on Monday night. We may be joined by some of your colleagues from the not online class. The Monday class may just join in on Monday night where we have a big review session, and I'll have a review sheet ready before that time for the final. We got lots of stuff to review. We've covered a decent amount of material this semester. Do you agree? I hope you've learned something this semester. I hope you feel like you've honed some of your logical capabilities. That's really what this class is about. It's about learning to be careful, be thorough, and to read, right? Read definition. So I've enjoyed having you. Any questions or comments? Well, we're running a little behind. I guess I will say good night. And there's an office hour. Today's Wednesday, so in 12 minutes there's an office hour. So if you have any questions about WebAssign, otherwise I'll see you soon. We'll have our regular Sunday office hour. We'll have the Monday review session, and then we'll probably have another office hour next Wednesday as well. So we'll keep our Wednesday and Sunday office hours until the final, okay?
Have a good rest of your night.
Thank you. Thanks for playing.
Have a good one.
You too. Thanks so much.